Okay, in this video I'd like to continue on my tutorials on thermodynamics and statistical mechanics. This is video number 38 and I'm going to discuss the chemical potential. So I'd like to draw your attention to my website universityphysicstutorials.com before we begin. So the previous videos to this are number 35 and 36, specifically number 36, because in both of these I discussed the thermodynamic identities, and in 36 is where we first came across the chemical potential. So a small bit of revision. In video number 36 we derived the following equation: that the chemical potential is minus the temperature, then the rate of change of entropy with respect to the number of particles, and we're holding both the internal energy and the volume fixed. Now, what does this mean? It means that the chemical potential is related to the number of particles. And that's the most important thing, is to relate to the number of particles. So if you're often, you say to yourself, well, what is the chemical potential? Think about it, it's related to the number of particles. Now, in order to have something in equilibrium or diffusive equilibrium, the chemical potential of A must be equal to the chemical potential of B. And we saw that, we saw for example that a system whose del S, del N is greater is going to have a smaller value of the chemical potential because of this negative term, and as a result is going to want to receive particles. Okay, it's going to want a flux of particles into it. But at equilibrium, the chemical potential of A is equal to the chemical potential of B. Okay, by definition. Now, the thermodynamic identity approved in video 36 was that the infinitesimal change of the total energy is TdS minus PdV plus mu dN. Okay, so this one here, this term here, is mechanical work. So we can draw an analogy here and say this is chemical work. Okay. Now, by the way, don't get bogged down on this particular formula here. It's not a big deal. Okay, but it's this. We're talking about the chemical potential is for chemical work, but it's related to the number of particles. Basically, actually, it's related to the conservation of the number of particles, as we will see in quantum statistics. So, where do we go from here? Well, if we fix the number of if I fix the volume and I fix the internal energy, then the thermodynamic identity becomes 0 is equal to TdS minus 0 times T. Oh, what am I doing? Sorry, plus 0, that's a plus, I'm just reading my notes incorrectly, plus mu dN. Or that mu is equal to minus T times del S del N. Okay, this is exactly what we thought a moment ago. But what happens if we this time instead fix the entropy and volume? Well, this time I'll let you do the derivatives yourself. You're going to find that the chemical potential is equal to plus del U del N at constant entropy and constant volume. Now, these sorts of things are important. To be able to work out your quantities using various other quantities is a very important thing to be able to do. So, can we just really write in English what the chemical potential is? I'm going to try my best to do this. Mu. The chemical potential is, mu has units of energy, the joule. Okay, you just look. I did it in the previous video number 36, but if you want, just look at the units on what we had. So that means mu is the amount by which a system's energy changes when you add one particle. Okay, Now the important point here is, in order to hold the entropy or multiplicity constant, mu must be negative. In order to hold the entropy or the multiplicity, constant, mu must be negative. Okay, so that should make sense. So we add a particle, therefore we need to have this negative term in order to be able to hold the entropy by, that's not a delta by the way, that's supposed to be S, the entropy or the multiplicity fixed. Alright, so that's all I've got to say about that. Thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also click on universityphysicstutorials.com.